Communication in the book is wild.
It really is, yeah.
Going from center to mass with differential equations.
And if you really looked at the rest of chapter 8, it's more just off the wall as well. There's a lot of weird stuff in there. It goes from center of mass to probability is in there. There's other stuff, but that's the big wild one as well.
Well, when you were talking about like, why would differential equations be useful? And it's like, you can model the whole like network packing of neurons. And like,
Yeah, yeah. It's kind of wild. That's what we're returning right back to on that problem. Yeah. Well, looks like we get to start. Welcome back, everyone. So I don't have a lot of announcements today other than we're going to finish off section 9.1 pretty shortly. Then we'll move into the second topic out of 3 that we're covering in chapter 9, dealing with the separable differential equations. And that's exactly what we solved in the very first problem up in section 9.1. When we wrote down the model, it was mostly because we were thinking with mathematical modeling, what is the differential equation? But we also just solved it. We literally used the technique in section 9.3 of separating out the part that is dt, the part that is p, and putting them together. So we'll take another close look at how all those go in section 9.3 with the application on this one is going to be for physics. But any questions at all, folks, before we get started today's work? Okay, let's get started then. We have one more topic to take a look into in section 9.1, and it's relative to this differential equation right here. The read-through says I don't know how to pronounce that, but I'm going to try. The Fish-Hugh-Nagumo model for the electrical impulse in a neuron states, in the absence of relaxation effects, I guess they're talking about something specific with neurology, I'm sure, the electrical potential in a neuron, which is going to be denoted by V of t, let's highlight that to just remind us of the context, obeys this differential equation. I notice the formatting of this is really kind of weird in a certain sense. Sometimes when people write down their differential equation, the formatting they leave it in is kind of informed by the neurology that told us what the model should look like. So it's got wild things like V never getting distributed in, that kind of stuff going on. Here they say A is a positive constant between 0 and 1. I'm not sure how they fine-tune that constant. But for this problem, we set it to 1/2. So we took the whole model, threw in a 1/2 there, and this is what we get, -3/2 plus 1/2. And this is the actual model that we're going to be working with. When it says, what are the equilibrium solutions? What we're referring to here are solutions, well, let's say it this way, and equilibrium, solution, satisfies dv dt is 0. So that's really all we're trying to solve with this for the equilibrium solution. We go to the differential equation, find out for what value of V is the whole first derivative of V itself. Remember, V is the potential in a neuron. When does that cause the whole differential equation itself to be 0? Stay at rest, in other words. Well, that's not too bad to solve. We just take this, throw a 0 in right here, and solve 0 equals -V multiplying V squared minus 3/2 V plus 1/2. And that will get us to those solutions. Solving this is kind of annoying in a certain sense because we'd probably default to factoring. So we need to factor out 1/2. We'll get, let's see here, -V halves, leaving behind. Factoring out a 1/2 always looks weird. This will turn into 2V squared minus 3V plus 1. Now that we have that, we can factor the thing in the middle here just a little bit more efficiently. 0 is equal to -V over 2. We'll get a 2V, V, And it looks like -1 on both of these. Let's double check. That'd be -2v minus v, hitting the -3v in the middle. So we've got a fully factored polynomial equation. We can just read off the solutions now. This implies on the very first factor, v is 0. Or on the second factor, we have v is 1/2. Or on the last factor, v equals 1. Now remember, all of these right here is the potential in a neuron. So we're saying an equilibrium solution is when the electrical potential or action potential, however they say it, is 0. Plug that 0 solution inside here, and then nothing changes. We just stay at 0 for all time. Another one's 1/2. Oh, geez. Take 1/2, plug it in right here. This whole thing becomes 0 again, and same story. So if the potential in the neuron, which is a bona fide function that varies, but if it happens to be any of these values, it stays on those values, is what we're saying with the so-called equilibrium part of the equilibrium solution. Not too different from when we were in section 9. Well, this is 9.1, from when we were in this problem up here, and we said, well, we can solve this, but notice there's one particular solution that's interesting. P equals 0 itself is a solution because it would make the right-hand side 0. That means you have a balance here of 0 derivative equaling a 0 function. And that's a population size. If it's at 0, it will just stay at 0 for all of time now. So same kind of thought on this one, but it's a more complicated differential equation. We had more equilibrium solutions on this one. Then the increasing-decreasing test comes into play. What's going on here is we haven't even solved this differential equation. We just have one, but we're wondering, if you produce a solution or a family of solutions, how would they behave? These are the equilibrium solutions, and now we can take the increasing-decreasing test to get a better view on all solutions to this differential equation. So let's capture this for a moment. And now we can answer for what values of v, that's a function itself, is v increasing? So what we do is really just a kind of a familiar algebraic technique. Take the number line. Now, as far as v being a potential in a neuron, it's an electrical potential. So for the electrical engineering-minded people in the classroom today, that means it could be negative or positive. Does that sound about right? That's something I'd probably want to Google just to be really sure and specific with. But we're not neurologists necessarily, so if we're not sure, then you know what? Let's just go with the possibility it's negative. And if we had to correct the model from there on out, we would. What we do next is we grab the equilibrium solutions. There's a value here at 0, a value at 1, value at 1/2. This is V for electric potential. And now that we have this partition right here, we can directly use that. This whole thing, dv dt. It's just in a factored form is all that we did to it. We didn't move any constants, multiply across 0 or anything like that. So this is exactly dv dt. And dv dt is the same thing as saying f prime of x. It's just a Leibniz notation, variables v and t, rather than x's and y's. So next, we can say here directly, if this value is increasing on an interval, or positive on an interval rather, that's the derivative being positive, then the function, the electrical potential, would be increasing on that interval. So the increasing-decreasing test from calculus is just directly relevant to differential equations. We can now break this into 4 regions for v prime, here, here, and here. We're thinking v prime on each one of these 4 different regions on the number line as corresponding to the f prime on this right here from the increasing-decreasing test. Here's the next slightly tedious part about it. You have to test your intervals, but there's some really quick tricks here. The powers on every one of these groups is odd, power 1. That means if we say increasing here greater than 0, it has to flip as an alternating pattern. The only thing that breaks an alternating power pattern is any even power, like a power 2. If it was, let's see, that power 2 is relative to 1/2. So if that really was squared, and we said b prime greater than 0 here, also greater than 0 here, it will match the same direction. But with all terms odd, or excuse me, all factors having an odd power, we really just need to test 1. Let's test at -1. Usually you want to use kind of a light color so you don't conflate this test point with an actual cut point on the diagram. So at -1, compute dv dt evaluate at v equals -1. The Leibniz notation is kind of impressively clunky, but it has its purpose, as crazy it is to look at. It says go over here, insert -1. I think I need more space for that. It's going to turn into, with a -1 here, that's a positive 1/2. -1 here is going to give us -3. And -1 here produces a -2, which is a positive sign. So altogether, it tells us directly b prime greater than 0 here, less than 0, greater than 0, less than 0. So we have that alternating pattern. Honestly, it's not a bad idea to plug in 2 and just double check. We did plug in 2, that's a negative times a positive times a positive. Yes, it would really be negative at the value 2 as a test point. At that point, I'm convinced, and here's the whole punchline to the increasing decreasing test. Wherever the derivative is positive, we wrote it as fv prime, but we're really thinking dv dt. We have that the function v itself is increasing. So if you start at a negative action potential, your solution to the differential equation increases towards the equilibrium solution 0. And once it gets there, it stays there. Here it's decreasing. And so now this tells us that this, as an equilibrium solution, is a stable point, in the sense that solutions converge towards it in that sense. If you're below, you increase towards it. If you're above, you decrease towards it. Over here, you're increasing. And that means this value is an unstable equilibrium point. If you are right at 1/2, the actual potential of the neuron is never going to change. But budget a little bit to the left, and it will change, it begins decreasing. Budget ever so slightly to the right, and it begins increasing instead. So this one is an unstable point. And then let's fill out the rest. It went increasing, then decreasing, giving us another stable point. So here is yet again, another stable equilibrium point. So we did it, folks. We used up the increasing, decreasing test from Calculus 1. Now we can answer part C for what values of V is V increasing. But we actually have a lot of information. For any solution to this differential equation, when we go to plot it, it's going to obey these kinds of properties right here. And the view on this is really kind of weird. It goes like this, really. So this axis flips around this way. That's the v-axis. Recall it's dv dt, right? So there's a t-axis going this way. We found equilibrium points at 0, 1/2, and 1. But they had different kinds of features. Some of them were stable, some of them were unstable. So let's convey that as well. Let's put in asymptotes. Well, this one at the unstable point is not an asymptote. It's something that repels the curve. So there they are. Now pick any solution to this differential equation. We're plotting them in blue, it looks like, with that circled. Let's just make that more apparent. There we go. If your solution starts off, say, maybe over here, we're between 0 and 1/2, it's got to now decrease in that kind of way. If it starts out down here, we're increasing, so it's begun doing something maybe like this. I don't know if I have the inflections on the curve, right? We would have to really solve this to know that part. if we start off, say, between 1/2 and 1, let me put that there just so I can see it better. Between 1/2 and 1, it's increasing, so it would go like this. Even if it's really close to 1/2, it's going to eventually increase up to that as a horizontal asymptote. And if it's way out here, this one would be decreasing. So we're stable here. All solution curves converge to it. Unstable at 1/2. That's an odd action potential. The only curve that stays on there is the curve that started at 1/2. Well, those are just the equilibriums. That's just one equilibrium solution, for example. And everywhere else, it's converging to other equilibrium solutions. So that's the one that repels, the rest of them attract. Differential equations are weird because now we get to use all sorts of stuff in calculus to know what's happening with the equation even before we solve it. There's a huge geometry saying what the solutions will do. There's infinitely many solutions, so we drew just a bunch of them, 4 altogether. Any questions at all, folks, with the diagram here or the associated diagram to the right? Oh, geez, that doesn't work. Here we go. Now for the larger question, or the actual official question, part C, all we want to know is what values of V are we increasing? So we can just say simply, for V in negative infinity up to 0, we're increasing union 1/2 to 1. Really, that's all we had to say. But if you know you're taking differential equations, this is a larger view of what's going on behind the scenes with this diagram right here. It's highly informative on how the solutions themselves behave. But we did it, folks. That's the conclusion of section 9.1. Whole goal here was to think about how differential equations come to be from mathematical modeling, how to tell you if you have a solution, and what would the solutions look like before you even go to solve the differential equation. That's essentially what we're doing with this problem here. But all that is not getting us to our main topic of actually ourselves solving those differential equations. So now we'll go to section 9.3 and make that happen. Any last questions at all, folks, before we conclude these notes? Okay, well, on to the separable differential equations. 9.3. One of the reasons we're not doing too many differential equations is it gets pretty involved pretty quickly. Just the second order differential equations, out of nowhere, linear algebra concepts make its way into that kind of content. So we're really just looking into solving the first order differential equations so that we're not going way outside the scope of calculus 2. But this is a very easy, or not, I shouldn't say very easy. This is a very approachable differential equation classification, the separable ones. It's first order, like we described, in which the expression for dy dx can be factored as a function of x times a function of y. This is the essence of being separable. So if your equation is separable, you could get it into that form somehow, some way. It also means the solutions for solving this would be actually separate it, go dy equals g of x, f of y, dy. It's not quite separated until we kick away f of y. Oh, hang on. Yeah, that should have been a dx on the right. Thanks for spotting that one. I was trying to visualize the dx being multiplied to the right-hand side. Then divide out your f of y. Dy will be equal to g of x dx. And thank goodness we have the right thing here. Without dx, we can't make any sense of that integration. And with y and dy, we can make sense of this one. And that's pretty much the whole method. Factor if necessary, separate, integrate, and then just solve whatever you have. Well, any questions, folks, before we go to try it out? Already on part A, one small problem is Newton's prime notation is not going to help us out in any way, shape, or form if we're trying to separate the equation. if you've got a y prime there, a really good call is immediately dive into Leibniz notation. So we'll write this in as y squared plus, actually, let's do a little bit better. Instead of just rewriting that out, let's do the factoring step as well. Y's and x's are mixed together, so we might as well start separating right here. Factor out y squared, leaves behind a 1 plus x. Now let's correct the notation here into Leibniz notation. Y prime transfers to dy dx. And now it's set to 1. At this point, we're really in this format where we have the y squared 1 plus x on the left-hand side, which is okay. We're going to move the dx over to the right and also divide 1 plus x to the right as well, so that we can get to this situation here. So we have y squared dy staying in position, multiply by dx, there it is on the far right, divide by 1 plus x, so 1 over 1 plus x. And if you wanted to, just integrate both right on this line. I find the notes are hard to kind of track if I do that right here. So for me personally, I'm going to put down a new line that goes like this. But if you prefer to just integrate right here, no harm done. I'll do it right here. And now we're just about ready to solve the whole differential equation. Kind of nice in a way. Some differential equations really don't take too much. And this is one of them. Next thing we do is ordinary antiderivative here gives us a third y cubed. Ordinary antiderivative here, this is basically a 1 over x. We get natural log, absolute value, 1 plus x. And because the derivative of 1 plus x is 1, there's no harm here with the chain rule. U substitution is not necessary on this one. Go plus c, and we still haven't solved the differential equation, but we have an implicit solution. What I mean by implicit solution is y is not exactly solved for until we have just y on the left-hand side. That would be the explicit solution that we're going for. So really not too much to do, right? The next thing to do is multiply both sides by 3. Y cubed is 3, natural log absolute value, 1 plus x, plus 3 times c, but if c is an arbitrary constant, so is 3 times c. So we'd usually, like in the last section, go c1, alert the reader that c1 is 3 times c so that everyone feels safe we didn't just drop something algebraically. But this conveys there's no new thing to really say here. It's just another arbitrary constant. Last step, just take the cube root of both sides. Y is equal to cube root 3 natural log 1 plus x in absolute value plus c1. And that's the total solution to the original differential equation. This has no context, so the real challenge here would be to try to describe what is the physical problem behind this one. But we'll do that kind of problem as the last problem on these notes as an application as well. Well, any last questions, folks, on finalizing this one? Okay, now, one thing to notice here, which is kind of interesting, now that we have the function, checking this equation is probably harder than solving it because we would have to square y, drop it into 2 spots, that's squaring this. We'd have to differentiate what we got, that's this one, who knows what that derivative is, plug it in all in this one spot and algebraically check, it simplifies to 1. That's actually, again, a lot more work than the original work of just solving this. Sometimes with differential equations, instead of trying to do the check, you just double check the forward process. But I'll leave it up to the class. Should we try to check it regardless? Like several saying no. Okay, I appreciate that. We'll leave this one just as it stands. So let's try out the next one very next then. This one's kind of weird as well, but this is more in an applied direction. When you're solving differential equations and there's a real context behind it, you can expect Leibniz shows up and the variable names are chosen to remind you about the problem. V might be a velocity, S might be, who knows, side length, time, something like that. Maybe a displacement from an original position. But this is what differential equations with applied stuff looks like. Kind of messy. And not quite separated. We can factor out an S in that denominator to really get it to that spot. Let's make that our first step. dv ds is s plus 1, factor out s, leaving v plus 1. This is going to allow us to now separate. We'll be able to take v plus 1, associate with dv over here, and ds goes with everything else. So here's our next step. Multiply v plus 1 on both sides of the equation so that, I'm just going to put in an x, v plus 1 dv is all we have on the left-hand side. Then multiply both sides by ds so that, let's see here, s plus 1 over s multiplies ds. At this stage, it's separated. Everything associated with v on one side, everything associated with s on one side. So on the next line, I'll go v plus 1 dv, but we're integrating it now. Integrating the right-hand side, but we might as well simplify. Let's divide s into everything to get 1 plus 1 over s ds. And all we need to do is an integration, and we'll be on our way. This one's a lot different than the last problem, though. In the last problem, we were able to solve for y directly, or we got the explicit solution. But I made a note in the homework. We can't always do that in a nice way. I mean, sometimes we can, but the effort of getting there is not worth getting the solution. Sometimes we want to leave our solution in implicit form, meaning we're not going to solve for y. It may be impossible or just algebraically prohibitive to be of any value to us. That's only going to happen on one exercise on the homework set. Exercise 7, kind of similar to this one. So let's put a quick note. We will leave the answer in implicit form. So let's go on and do just that. Antiderivative over here kind of informs why we're doing that. We are getting v squared plus v on the left-hand side. Right-hand side, we get s plus natural log absolute value of s plus a constant. And yeah, you can solve for v, move this whole thing to the left and quadratic formula. Yeah, go ahead. Oh, sorry for that. Thanks for munching it. That should have been a 1/2 on there. Other questions so far? Looking for other errors. Usually if you find one mistake, there's a strong chance for another one. Okay, I think we're on the better track there. So this is a set of solutions. There's really infinitely many because of this c right here. But even if c is 0, there's more than one solution. Power 2 right here, when we go to take a square root, if we did solve for v, is going to give us a plus and a minus square root on the right-hand side. Or if we move this whole thing to the left, we can use the quadratic formula, which gives two solutions again. But the quadratic formula specifying these solutions is starting to get so complicated. This might be the preferable solution to express. So here it is. The general solution in implicit form. Definitely kind of weird. This is a feature of separable equations. Once we get to this step, not always an easy road to solve what we got. Section 9.5 goes differently. The first ordered linear differential equations doesn't have this feature. We have a way to specify the solution that takes us to the direct and unique solution each and every time. But here, sometimes these can be painful algebraically, and so that's why we're stopping on this one. Any questions at the moment, folks, with what we got on this? Okay, and now it's extra weird because you might ask yourself, if we really had to verify we have a solution to that differential equation, how would we even check it? We didn't solve, but then you would go back way back to Calculus 1, Chapter 3, and do implicit differentiation on that. We have an implicit function, really two of them are in there. We can differentiate this implicitly, and then double check if we have a solution to the original equation. Again, it's a lot of work. We're going to emphasize mainly solving the equations, but it's good to mention what would checking them even look like if we had to. But here's the next one down the line, part C. Any questions at the moment before we take a look at that one? Okay. Part C looks like it has a lot going on out of nowhere. Let me make sure we have enough space to solve that one. Y cubed dy dx, y4 plus 1 cosine x. At least the variables are kind of normal. So for dy, we have y cubed y4 plus 1. Y is already on the correct side. For dx, we have cosine x. Oh, hang on. Well, this part for y is not. I didn't see that equality too clearly. We need to multiply by dx, divide by y power 4 plus 1, and that will take us where we need to be. So first on the left, we have y cubed, but divide by this, y power 4 plus 1. Leave dy right in that position, and it's going to be set equal to, on the right is just cosine x. We're multiplying it against dx from that denominator. And if we can integrate all of this, we're in business. It's now separated. So we're integrating y cubed, y power 4 plus 1, dy. And the nicer integral is integrate cosine x, dx. So that's all it's left to do. Two integrals. This one's a little bit rougher, but not too bad. It looks like a u substitution. And this one is just a sine x. So for the integral on the left, let's say take u is y power 4 plus 1. Take its differential right away. Not too different than what we did over here. This is just a different differential, in other words. Differential down here is du, 4y cubed dy. So a fourth du is y cubed dy, and we can now take out all of that, dropping in a fourth y. So let's go to the right since I kind of broke the formatting going down. For this portion right here, we are getting 1/4 integral of 1 over u du. So here's the portion coming from there, substituted in, equals antiderivative of cosine x dx. So on the left, it's 1/4 natural log absolute value of u. On the right, this is always tricky. Is this a positive sign or a negative sign? Any volunteers? Good call. That one's positive sign. Add the constant c. And even though the complexity of this differential equation seems a lot higher, there's a polynomial of degree 4, a trigonometric function. This one looked like it just had linear portions, but that's the harder one up there in part B. This one we can solve for. This is what's weird about differential equations. Whether you can solve for an explicit solution, or you're forced into an implicit one, it is not always easy to spot just based on the equation itself. But back down here on this one, if we are to solve this, we have a couple things we need to do first. Undo the substitution and multiply by 4. Let's do both at once. Natural log of y power 4, not x, plus 1, dropping absolute values since that's a positive quantity, is 4 sine x plus c1, where c1 is 4c. Now we need to undo the logarithm, but that just means we raise both sides to power e. So e natural log y power 4 plus 1. This is a skippable step if you wanted to go directly to the result, but this just informs in the notes what's going on, so a little bit of extra writing. On the left, we have a good old cancellation for inverse functions, leaving y power 4 plus 1. On the right, no such cancellation, but we can take e power c1, split it off in this way, and leave behind e power 4 sine x. Kind of a weird equation that we're getting. but we're nearly there. Subtract 1. Y power 4 is e to the power c1, e to the power 4 sine x, minus 1. And last thing to do, take the fourth root of both sides. But it's an even root, so when you do that, you will be including a positive or negative result on the right-hand side. So y, or you could call it y of x if you want to emphasize function notation. I'll just go with the y, is positive or negative of the fourth root. Let me try again with that formatting. Positive or negative of the fourth root of e power c1, e power 4 sine x. Well, we got it, folks. Any questions on this right here?
What
This
happened to the
last-
-1?
Oh, great question. Looks like it just got totally neglected. Thanks for spotting that. -1 should carry down right here as well. Let me highlight that just for extra emphasis. Other questions so far? Okay. One question I would have looking at this is some of the steps we take just do not seem consistent, aside from the fact that this is all weird differential equation stuff. What I mean is, from over here, we multiply both sides by 4, got 4 sine x plus a c1. So we use that right there just to simplify into a new arbitrary constant. But we never did it over here with e power c1. We left it directly in that format. We don't want to put c2 here, in other words. If we did, it could be a huge misconception on the nature of these solutions. And the reason for that is e to the power of c1 is strictly greater than 0. So leaving it in this format is just a way to alert the reader that is a non-negative constant right there. If we put c2 equals e power c1 in this whole position, people could read through, maybe miss this part and think any real number goes there, but it's not the case. It has to be strictly non-negative numbers. So leaving it in this way reinforces that in this particular way of writing the answer. Well, that's 3 differential equations so far that we solved today, some of them weirder than others. At least this one is an explicit solution. Actually, this is the weird one where we're just forced to leave it as an implicit solution. Well, we'll try out another class of differential equations coming up next. But notice the weird thing about these. This is called down here a general solution. Because this is really not one solution. It's a whole infinite family of solutions indexed by a positive real number from right here. Well, sometimes we don't want a general solution. Sometimes we want one exact function that's going to solve the differential equation and whatever initial values that we specify about the solution. And that's what's going on down here. On example 2, we're solving a differential equation, but we're further requiring that our constant satisfies this. We're not getting a general solution. We are getting the solution, and we get to say the solution this time. There's only one to the initial value problem. So here's our next adventure to take a look at. Looking at the format, biggest problem in my opinion is we want to correct and bring back Leibniz notation where we see the y prime. So this can be rewritten as 2 root x dy dx is cosine squared y. Okay, we're on a good first step. Dy is going to take and grab cosine squared y, put it in the same spot. And dx is going to follow along with 2 root x. So first, let's divide by cosine squared y. Keep in mind with trigonometry, if you divide by cosine squared, it becomes secant squared. So now it's secant squared y dy on the left-hand side. On the right, this one's a little bit more annoying, I'd say. We have dx moving to the right. But then we're also dividing by 2, so here's the 1/2. We're dividing by root x, so here is, let's just go 1 over 2 root x. And we'll fix that exponent here on our next step when we actually go to integrate this. So on the left, secant power 1 is the weird one. That's the one that requires a specialty antiderivative, commonly found on the last sheet of an exam. But secant squared is the good one. We can integrate that one immediately. So secant squared y dy equals, here we have a coefficient of 1/2 that we can separate out as a constant. X to power 1/2 in the denominator becomes x power negative 1/2 dx. So we're on our way. Anyone happen to spot antiderivative here? Good call. Derivative of tangent is the secant squared. So just tangent y on the left. On the right, not as bad either. We'll go 1/2. X goes up by 1 power, so 1/2. Reciprocal is times 2 now. And add a constant. So we get that tangent y is square root x plus the constant c. But that's the general solution to the original differential equation. Infinitely many different functions indexed by the real number c, not what we wanted. So we come back over here, and this is the next level of steps. We solve for the coefficient c, or constant of integration c next. Let's just bring this down. Y at 4 equals pi over 4 implies x equals 4, y equals pi over 4. You don't need to write it in that line, but sometimes throwing in function notation next to y, when you usually write y equals f of x, just looks strange. Oh, let me double check the chat. How do we make C1? Oh, sorry, how do we know what to make C1? I think you're referring to, sorry, I missed that chat earlier, this step right here. And on that question there, to know what to make C1, the 4C, it was really when we went to multiply 4, it multiplied over here, and it multiplied here as well to get us a 4C. And that's what informed us what C1 should have been. We just set it equal to the 4 that would have emerged right in that spot. And you know what? Now that you mention it, that's kind of hard to see in the notes that I wrote out. Let me see if I can insert one additional line here. 1/4 natural log u means natural log absolute value of u is 4 sine x plus 4c. And then I think this is the better way to answer your question. Whatever we saw here, we just redefined as C1 right down below. Now back to our other problem right over here. Y at 4 equals pi over 4 implies this information. And that's something we can just directly substitute into the equation on the left. Go tangent at y set to pi over 4, suspiciously chosen to make this a fast computation, equals the square root of x, becoming square root of 4, plus c. Tangent at pi over 4 is exactly 1. So 1 equals 2 plus c, which means the one and only one function that solves the differential equation and the initialized value that at 4 we get pi over 4 is found by just throwing a -1 here for c. So we'll say, therefore, well, we're not quite there. Let's not do the therefore yet. Let's say tangent y equals root x minus 1. All I've achieved in this step is solve for the coefficient, or I keep saying coefficient, solve for the constant of integration c is a better way to say that. Other questions so far? Okay, I wanted to celebrate right here. It felt done, but it's not done. Anyone say what the last step should be? It's kind of like this problem way up here, right? Oh, not that one. This one, we just aborted any future steps because we analyzed the format of how v came in 2 terms and decided not worth hitting the quadratic formula on this whole expression. More abstract than necessary. Kind of what's going on with this one, except you can invert that. You go y equals tangent inverse or arctangent, root x minus 1. So that would give us the explicit solution on this one. If you forgot to do that last step, it wouldn't be the end of the world. If this is a 5-point homework problem, that's like 1 point. The constant might be worth more because that's the major feature of what this is. Solving for the constant, I guess, worth 2 points isn't too major either. Always try to get the explicit solution when you can, and only abort if it looks like the algebra is going ugly. For a hint on the homework, that's problem number 7 in section 9.3 is where it gets ugly. So that's solving initial value problems. And because that was so fun, let's try it out all over again. This one again looks like we're dealing with an applied situation with the non-standard variables. And there's a proportionality constant as well. Yeah, go ahead. Therefore, oh, right over here. Yeah, that's what I was wanting to put here. More of a conclusion statement, but yeah, thanks for mentioning that. Yeah, absolutely. Usually I put those little triangles as a therefore, just as an alternative way to say something like that, expressing my solution as definitely being in that spot. Boxes are great. I like the triangles because it just feels fancy, for the only reason. Other questions at the moment? Okay, thanks for mentioning that. I think it was worthy on this one because if it feels like your work is just a cloud of mathematics, you do sometimes want to direct either with a box, a therefore, or even something like this. All this work implies that y is equal to. Anything fancy to kind of convey your solution a little bit better is a good idea. And sometimes we can't get away with this. Math just gets messy. And speaking of messy, this one looks pretty bad as well. Let's give it a try. I think the really nasty part about this is k. I said it's a constant, but we have to justify that. There's no context to tell us it's a constant, but Leibniz notation is what's doing it for us. If it goes dl dt, that means L is going to be the dependent variable, T is going to be the independent variable, and everything else is constant. So this informs us K is a constant. Then from here on out, just leave K wherever you would like, wherever it's most convenient. I'll just keep it on the right-hand side. There's an L squared here. We need to move over to the left. Natural log T can stay right in that position. And here's those typical steps. I'm dividing by L squared, so here's 1 over L squared here. Staying with DL equals K, just staying in that position. Natural log T is also not moving. Then multiply both sides by the dt down here. And looks to my eye like we've separated it at that stage. Any questions, folks, to getting to that step? Okay, next we integrate both sides. So I'll call the left-hand side. Let's integrate not 1 over L squared, but L power -2, just my preferred way of visualizing it. If you're great at finding an antiderivative in this form, -1 over L, then you don't have to do that. Over here on the right, because K is a constant, I'm going to visualize it this way. Integrate natural log T dt. And there's that one integral that we've mentioned a lot. This one shows up on a formula sheet at the end of the exams, not because it isn't a worthy problem to do. It's because the author did this in section 7.1. We did it ourselves, and we don't need to keep on doing it every time it occurs. Antiderivative of natural log T, you're always welcome to take for granted as T, natural log T. Anyone remember the last part? Good call, minus a T, and you've got it. So we're just going to apply that here on the right-hand side. No reason to reinvent the wheel is the thought here. On the left, power becomes -1. So we multiply by -1, and we get K. Antiderivative on this is T natural log T minus T plus the constant C, and we're just about there. Now, there's a lot of styles to solving the constant of integration through that initial condition here. I think for most problems, if you solved it right on this step, Sometimes it does make the algebra just a little bit easier to maneuver through. So usually that's the way I like to go with these. Let's take this. I'm going to rewrite it as L of 1 equals -1. Just for the sake of being explicit with what this is saying, I'm going to write out this means t is 1. L itself is going to output -1 when t is 1, and drop that information here. -1 in that spot goes negative of -1 to power -1. That's two negative signs, really. The exponent being negative doesn't give us another multiplication by -1, just positive on the left. On the right, we have k, t is 1, so 1 natural log 1 minus 1 plus a constant. So that's the whole equation on the left with this information input. Left-hand side is +1 equals, whole thing here is 0. So this is just k, let me fix that. K times 0 minus 1, let's just write it in as a negative k, plus the constant c. So 1 plus k is c. We've got our value for c, we'll just throw that in and keep on going forward in the solution for this up here. Any questions at the moment, folks, so far? Okay, let's keep on going. So on the left, I'm going to write this in as -1 over L, anticipating solving this directly for L. Here it's going to be k, t, natural log t minus t. Then over here, +1 plus k. Now here's the next fun trick with algebra. If you have L in the denominator, no problem. Take the reciprocal of the left-hand side, and then take the reciprocal of the entire right-hand side. So that's a nice little kind of a mathematical backflip there. The logic on what's really happening here is you're taking a cross product of both sides simultaneously, essentially, to get this result down below. Now, last thing to do, move the negative sign over. We have L is -1 over k, t, natural log t minus t plus 1 plus k. That's a lot of writing. And that's our solution, finally, to the original differential equation. Well, I said that weird. That's the solution to the initial value problem is a better way to say it, because it was a differential equation with the initial condition, leading to directly one and only one unique equation. Sort of. This equation still depends on whatever k was. So if k can vary, then, well, we still have a family of potential solutions as well in this problem. But we did it, folks. That's kind of a more abstract one, thanks to the variables being non-standard. For the next one, we're going to look into the applied problem, but any questions at the moment? Okay, well, here's our last problem for the day, almost to the weekend, folks. And the applied problem is from physics, but this is a pretty interesting physical problem. Starts off by saying, object of mass m is moving horizontally through a medium which resists the motion with a force that is a function of the actual velocity it's moving in. And this is what that would convey. That's a lot of wording. But let me skip down to here. For example, to match up this physical situation, imagine a boat moving through water. So whatever its velocity is, the water itself is going to resist its forward motion. Greater and greater, the higher the velocity. So here's how we try to capture this information in a differential equation. It says, resist the motion with the force that's a function of its velocity. Well, the force is going to be the mass times acceleration. Acceleration is the second derivative of the position function, s equals s of t. But the second derivative of the position function is the first derivative of the velocity function. So acceleration jumps to its legitimate expression, second order derivative. The complexity got reduced because derivative of s gives us velocity. So we have dv dt here. And finally, let's see what this was saying again. Object of mass m moves horizontally through a medium which resists the motion with the force that is a function of the velocity. What they're really talking about is this part right here. That's the differential equation under consideration, and it could be reformatted as m dv dt minus f of v equals 0. Only reason you want to reformat it that way is when it says resist the motion, we're talking about a function, force function, that's f, subtracted away from mass times dv dt. So that gives us a differential equation. We'll still leave it in this format, but this is how it was modeled in this way from the original statement. Okay, so we've got all that so far. Applied problems are really messy, and sometimes there's just a lot of physical intuition or physical properties from physics we have to kind of maneuver through till we get to the punchline right here. And it says next, the problem changes a little bit again. Suppose that the resisting force is proportional to the velocity. That means force at v is equal to negative k times v, and k is a positive constant. So if that's the case, we can take this whole equation right here, re-express it again as mass dv dt equals, and throw in this spot, or this bit right here, f of v, which is now equal to negative kv. We were directly told this time k is a positive constant, so that will help us with integrating. And mass, we were probably thinking as a positive constant as well, which is also weird with physics. If we have velocity that's too high, mass changes as a function of velocity and it's no longer constant. That's unfortunate. But here we said this model is appropriate for small values of the velocity. In other words, think of the boat moving through the water. This is a rowboat, not a motor boat, what we're trying to model here. So velocities are small, and that implies mass itself is constant. It's not going to fluctuate based off a massive velocity. It says next, determine v at any time t, but that's just a way of saying solve this differential equation right here. So it's a useful model, even though it's a limited model. It says it right away here as a kind of a catch-all statement without defining what small is. That's kind of unfortunate. But let's go ahead and solve this regardless with what we have. So we have dv. We can move everything over with dv, but let me actually write it in this way. I don't think there's any need to move over a constant. You can just leave your constant directly where it is. No harm there. And next, for dt, there is no t in this problem. So when we go to integrate, that's going to be even nicer. This next line is then mass. We're going to, let's see, divide by v. So times 1 over v. Leave dv right where it is equal to negative k times dt. So now we integrate both sides at this stage. The integral on the left can be visualized as mass, integrate 1 over v dv. Integral on the right could be visualized as negative k, integrate 1 dt. And not too wild as far as the integrals go. Really the hard thing about an applied problem like this is taking all of this information and getting down to the punchline that you're just solving that differential equation. Would have been nice if they told us that on the onset, but again, this is how physical applications often go. It's a mess we read through so we can try to extract the relevant part out of it. So last step, mass is the natural logarithm of v from this step, or that spot. Right-hand side is going to be negative kt plus a constant. There is no initial condition here, so we're solving this as any kind of family of function. And how should we go forward? Well, we could divide by m. It's allowed. We would not have mass 0 in this problem, right? It would make no sense. So natural log absolute value of v. is negative k over m t plus c over m. But here on the next step, we can just redefine C1 is C over M. Because if C is an arbitrary constant and M is not zero, C over M is just as arbitrary. This can be any real number just as well. So on the left-hand side, we'll go E natural log absolute value V, E to the power of all of this stuff, negative KT divided by M plus C1. So here's where we just re-expressed our constant in that format. Last steps are cancel that right there. So that absolute value V is still here. And let's think about the absolute value V. Would you say that the velocity has to be positive? Well, positive just means you're going in a forward direction. Negative velocity means you're going in a backward direction. Would this still apply if we're going backwards? I don't know if that would be a big deal. This just has to resist the motion or resist the velocity. It didn't say what the sign of the velocity had to be. And these problems are really weird. It's a physics problem only tracked in one dimension. Being positive either means it's going to the left or to the right or up or down. It's not being very informative. So I think we should allow V to be negative on this one. That's just my personal interpretation of the physical problem. If that's the case, we do need to take an extra step in eliminating that absolute value. That's just as well. We should see how that goes. So let's make that our next step. We have e to the power of C1, e to the negative KT over M. When we go to solve this, we get V is plus or minus e power C1, e power negative KT over M. And now that's a really built up constant. Plus or minus e to the C1 is almost every real number, but it cannot ever be zero. So plus or minus e to the C1 is non-zero. It can be everything else. But now we should be suspicious. Is V equals zero a solution to this? It actually looks like it. This happened in the section 9.1 notes. V equals zero is a particular solution. We argued that V should be allowed to be negative. We are often thinking of it as positive, but if it's zero, well, that would just mean the velocity is zero over here, and the f of V function, which became negative kV, zero here as well. It actually bounces as a differential equation, zero equals zero. So there's an extra solution that we can combine with this. Since zero is a solution, we can now say, therefore, V equals C2, yet another constant, E negative KT over M, where C2 is in R. It can now be any real number whatsoever. And R is just a different way of saying all real numbers, or interval notation, negative infinity to positive infinity. So this is kind of a weird problem. It would make a horrendously bad exam problem because there's a lot to digest to even get started. And then when you think more and more about the problem, our solution gets bigger and bigger and bigger because we're allowing this coefficient all of a sudden thinking of it as positive, allowing it to be positive or negative, but non-zero, to why not let it be zero? It fits in the problem just fine. Differential equations are weird in that kind of sense. It's not always obvious what the form should take. You have to constantly think about the context and wonder, is this allowed through the context? But we did it, folks. That's separable differential equations. Any questions about them? Okay, next time when we come back on Monday, we're going for the first order linear differential equations. And the excitement with that one is, all we're really doing is reversing the product rule directly, not like integration by parts. We're literally just taking the formula for product rule, going backwards, and then integrating. It's kind of a fun little technique. But we'll take a look at that to next time. Have a great night, folks. If you have any questions, I'll be happy to help out. Otherwise, I'll see you next Monday. Yep, have a good one.